So good morning, everyone. You can hear me? Yes? Okay, good. So I'm Claudia Cardoso. I work here in Modena in the Ciarnano Institute. And I will talk about some concepts that will lead to the actual GW calculation. So I'll talk about quasiparticles, screened interactions, and hopefully we will arrive to the GW approximation. So what is the framework of this talk? So before Andrea Marini gave like an introduction to many-body perturbation theory, talked about Feynman diagrams, and now we'll get closer and closer to the actual calculation, to the actual GW calculation, and maybe we can, during this morning, answer the question that was done before in a more concrete way. So let's see how it goes. I will talk about some concepts of the GW approximation, and afterwards, Alberto Guandalini and Giacomo Sesti will talk about the actual equations that we have to solve and how do we solve these calculations to get quasi-particle band structure, for example. Okay, so let's start from a system of n interacting electrons. And we have this Hamiltonian that we can separate in several terms. We have, for instance, a kinetic energy, an interaction with an external potential that can be due, for example, to the ions in a crystal. And then we have our electrons that interact through the Coulomb potential. And this is the two-body interaction that gives us a bit of trouble when trying to solve this system. So we have seen what are the Green functions. We have the one particle Green function here written as a time-ordered Green function. And in this object, in the Green function, we have lots of information. We have the ground state energy, but we also have the expectation value of other single particle operators on the ground states. But as we will see, we can extract from these objects the single particle excitation spectrum. That is, in the end, what we are interested in. So this is an expectation value of two field operators, a creation and annihilation operator. And since we have it here in the time-ordered form, we have two terms that in which the time instance that we consider, the order of the time instance, determine the order of these creating and annihilation operators. So, to which corresponds these two terms? So we can say that this first term gives us the propagation of an added electron in our system. So we create at time t prime, at r prime, an electron that then propagates in our system and then is annihilated at a second moment t in a different place. While the second term gives us the propagation of a hole. So we destroy an electron at some point, this hole propagates, and then it disappears again in a different time, in a different place. So why is this time-ordered Green function useful? Because we can insert, so this is our original expression, and we can insert in the middle of these two operators, the creation and annihilation operators, the completeness identities. So we can insert a sum in states of a system that has -1 or +1 electron. So we just picked our time-ordered Green function. We inserted this sum in these states. So this is just the same expression. And now we can go from the time space to the frequency space through a Fourier transform. So we have that this field operators depends on time, and also these theta functions that give us the time ordering. And we can write the one particle green function in the frequency space. So when we look at this expression, we see again a sum, and then we see two terms that in the denominator now have the energies of, so the ground state energy of the system with an electrons, and we have also the energies of excited states of the system with -1 and +1 electron. So we have this green function that has two terms that in the denominator we have the energy differences between these two states. The ground state with n electrons and an excited state with n-1 electrons, and the same with an extra electron. Okay, so this is useful because in this way, the green function will tell us something about these processes here. So this will give us information about the process where we extract an electron from our system, or we add an electron to our system. And if we look closer at the structure of this green function, and we plot so when the green function gets to a frequency or to an energy that is equal to this difference, the denominator is 0. So this means that we have poles at these points here. And if we plot the poles of the green function, so the poles of the green functions give us these energy differences, we see that, so this is the frequency plane, a complex frequency plane. These poles will be infinitely close to the real axis because we have this limit here, and will be above the real axis for this term here with n-1 particles, and below the real axis for this element here. So we see that the poles of the green function give us these energy differences that we were looking for. And this is useful because it's exactly what is measured in photoemission. So in photoemission, if we want to probe the valence or the conduction states of a system, we can use direct or inverse photoemission, where we shine, in the case of direct photoemission, we shine light in a system to extract an electron, and the energy, so then we measure the energy of this electron, and it will give us information about the original state. In inverse photoemission, that is a less common technique, but still used, we inject an electron and then it will decay, and the system will emit light, and that light will give us information about the valence states of our system. So more precisely, if we look at direct photoemission, we have an electron that's in a certain occupied state. We shine light that we know the energy of this incoming light. This electron will overcome the work function, will go to the vacuum, will get away from our system, and the kinetic energy of this system, of this electron, will allow us to compute this energy difference that is the ionization potential. In case of the inverse photoemission, we have the same thing. We add an electron that will occupy an excited state of the system, and then when it decays, it will emit light. We can measure this light, and we get, so from the energy of the incoming electron and the light emitted by the system, we can compute the energy difference, this energy difference here that corresponds to the electron affinity. So at this point, I would just to make to stress the difference between, because until now we are talking about this kind of excitations, and these are charged excitations, and this is the kind of process that is treated in the GW approximation that we are talking today. There are, of course, other type of excitation, so we can excite an electron from an occupied state to an empty valence state, but the electron doesn't get away from the system. And in this case, we'll have like an electron hole pair, and we have to take care of the interaction between these two objects. So this is the object of the GW approximation, that in most cases it's enough to use the one particle Green function to study these processes. In the case of neutral excitations, we'll have to go a bit further. Often we have to include this type of interactions that are called excitonic effects, and we'll have to use the beta-Salpeter equation that will be talked about in the next days. So these are two different frameworks that we'll choose within the school. Okay, so going back to our direct photoemission experiment, so we shine light in a system, and then we have to measure a current, a photocurrent, and this photocurrent can be computed using the Fermi's golden rule that is given by this expression here, where we have the final state of the system, the energy of the outcoming electron, the energy of the light we are using to shine on the system, and using some approximations, as usual, there are always approximations involved, we can write this photocurrent in this form here, where we have some matrix elements, but we have this object here that is called the spectral function, and we'll see it will be important in the next steps. And this spectral function is given by this expression here that is a sum on the occupied states of these elements here. So this spectral function can be directly obtained from the Green function. So the spectral function that we can obtain from photoemission can be obtained directly from the Green function. So it corresponds to the imaginary part of the Green function. And so if we compute the imaginary part of the Green function, we see that we have precisely the same expression of the spectral function that we saw before for the photoemission experiment, where we have these elements here, these F elements that we've seen before. And the spectral function has inside many information about the excitations, but if we do R equal to R prime, and so if we do the diagonal terms of this spectral function will obtain the density of states of our many-body system. So this is, as we'll see, this spectral function, as we'll see, has an important role in our GW approximation. So the photoemission spectroscopy, and especially the angle-resolved photoemission spectroscopy, so if we can obtain all those quantities I talked about resolved in the K space, in the reciprocal space, is very close to the GW approximation and to the Green function. So it's the most direct method of studying electronic structure of solids, and provides information of the single particle Green's function, which can be calculated starting from a microscopic Hamiltonian. So this is the counterpart, the experimental counterpart of the GW calculation. So we will always compare our results, or we'll often compare our results with angle resolved photoemission. Okay, so let's look again at the photoemission measurement, and let's compare with the calculation, let's say the non-interacting calculation. Here we have a band structure, DFT band structure. That's, as we have seen, is it's not so it's a ground state property of our system, and here we have a measurement of that comes from angle resolved photoemission, and you can see that there are some differences. The main difference that I want to stress is that while our DFT band structure is made of these lines that have no width, in a photoemission experiment we can see that the band structure So besides these lines that we can follow, has broadenings as structures that are not described by a DFT calculation. So in a let's say if we have the spectral function of a non-interacting system, we'll have these clean lines that we've seen in the DFT band structure. So the excitations correspond to delta peaks. So this is a cut of the band structure along the energy and here along the K-space. And we'll have each excitation gives a peak, a delta peak with no broadening. If we look at the spectral function given for an interacting system, a many-body interacting system, we have a completely different thing. So these delta peaks now are broader, and they are not the only structures that we can see in the spectral function. So we can see that they get broader when we get away from the Fermi energy, and we'll try to understand what is the structure of the interacting quasi-particle system means. So let's go back a little bit. We've seen that we can write the green function. You remember the green function was written this lemon representation. It had two terms that here I collapsed into one, where there are these, and the green function has these pools in energies that are energy differences between with n and plus one or n minus one electrons. And we've seen that this corresponds to poles in the frequency plane that are very close to the real axis. If we plot the spectral function, these poles will give rise to many delta peaks that have this shape. So we see that if we consider that each of these peaks corresponds to an excitation, we have much more peaks than we had states in our DFT calculation. So we have infinitely more excitations because this is our this is an interactive system and there are complicated processes going on. So we want to try. This is, however, a little bit difficult to relate with the picture that we are used to. So what can we do? We can see that these poles that are very close together form an envelope that defines a certain structure. So we can somehow think of reformulating our green function, and instead of having a series of these delta peaks, we want now to rewrite this green function in a way that it gives us a distribution. So one peak, just one peak, and that corresponds to the envelope of this series of peaks, and is now a little bit different from before. So what is the difference? It has a broadening. So as I said, it has a broadening. We can write it in this way. So now we are using what we will call quasi-particle orbitals. It has one pole, but this pole is now not close to the real axis. It has an imaginary component, and this imaginary component gives the broadening of this peak. So, not work? Ah, okay. So we want to do this reformulation of our green function when we have a representation. So let's think of this as our Schrödinger equation, and we have this potential that we'll call self-energy, and it will appear again in the next slides. And we had this green function that had a very large number of poles that were given by this energy here, and we want to reformulate our problem in a different system that we call a quasi-particle system that now has less poles. So the number of these energies is much smaller than these ones, and of course we pay. So what we have to pay to do this simplification is that now we have these energies that are complex, and this self-energy, our potential that we're considering here, is now non-emission and frequency dependent. So it's a very complex object. But still, this gives a picture that it's simpler to interpret when we look at the results of or when we look at a grid function. So if we again go back to our spectral function, we can see that again under certain approximations, we can write the spectral function as a function of this self-energy that we'll introduce better lately, and this self-energy carries the information of the structure that we have seen in the photo emission measurement. So the imaginary part of the self-energy gives the broadening, and this is also related to the lifetime of the excitation. So if we have, imagine that to excite an electron, it is excited in a high energy state, it can decay to lower energy states. So it will have a small lifetime. If it is excited to a state that is closer to the Fermi energy, it will not decay to lower energy states, so it will have a larger lifetime. So the lifetimes will be larger, closer to the Fermi energy, and in that case, we'll have like a delta function. This broadening will be much smaller. The real part of this self-energy, that we reduce the number of volts, remember, so the self-energy now can be seen as a correction. So our new energy is a shift given by the real part of the self-energy with respect to the delta function that we had in the non-interacting system. And because this self-energy is frequency dependent, we'll have these extra structures that we call satellites, and this renormalization factor Z that is related precisely with the dependence of the self-energy in the frequency, give us the spectral weight, so the area below this peak. It means that if this area is slower, then we'll have a larger weight of the extra structures of these satellites. Okay, so we have done this reformulation into quasi-particle energies, into quasi-particles. So what we have is that we can see our quasi-particle as our original particle dressed with the induced changes in the vicinity of our quasi-particle. So we are not looking at the original electron, but also at the changes it induces in its vicinity. And it's convenient to think of the interaction between quasi-particles, to treat the interaction of these quasi-particles not with the Coulomb interaction, but precisely with an interaction that is screened by the other electrons, by the other particles in our medium. And here, maybe this was treated yesterday. So how do we do this? We have this perturbation. Let's say we have a hole in a certain place. That is our perturbation. It will induce a charge in the vicinity that is related with the density response function of our system. This response function defines a dielectric function, and in its turn, it's possible to define a screened interaction, this W, that is the original Coulomb interaction screened by the induced charges in the vicinity of our original charge. So these are the two main ingredients of the GW approximation: quasi-particles and the screen. Let's say the green function of the quasi-particles that gives the G of the GW interaction, and then the screen Coulomb interaction that is this W. And why is this useful? Because we are doing perturbation theory. And as you can see intuitively, this interaction is much weaker than the bare Coulomb interaction, so it will be easier to treat as a perturbation, and it will be easier to insert in a many-body perturbation theory. Okay, so these are the main ingredients of our GW3. So let's go back to the many-body perturbation theory that Andrea Marini introduced before. We have our system with a kinetic energy, an external potential, and a two-body interaction that can be the Coulomb interaction or a screen interaction. And we have our grid function that gives the propagation of a particle, and it can be written like this. And within this path, many things can happen to this particle. So we can suffer different scattering events that are represented here by this symbol. So in case of, if we take into account, if we say that our scattering events are given by the interaction, the two-body Coulomb interaction, then we can write our green function as an expansion of this type of diagrams as Andreas shown before. So using all the machinery of many-body perturbation theory, we can do an expansion of this one particle interacting green function, and we can rewrite it in a way that depends. So in a way that gives this the Dyson equation. So we have our one particle green function for the interacting system that can be written in terms of the green function of a non-interacting system, and then all the scattering events summarized or included in this self-energy that can be expanded with the Feynman diagrams describing the several types of scattering events that can happen. So when we choose the scattering events that we include in our self-energy, we have different approximations, as was said before. So if we include these first two diagrams, we'll have the artery fog. And if we include different diagrams, we'll have different approximations. So I know this was a little bit fast, but then afterwards, Alberto Gondalini and Giacomo will tell the story much in a slower way. So in 1965, Edin introduced a new method to compute this, our famous now one particle green function. And so he uses a perturbation theory, but as he says in the text, he makes an expansion in terms of the screen potential that we have seen before. So instead of using the Coulomb potential, for the reasons that I said before, so the screen potential is much weaker and it's much easier to treat as a perturbation. And he introduced again a series of diagrams for the self-energy that equals m here. So what are the Edin's equations? The Edin's equations are a set of closed equations. So they are supposed to be solved iteratively, where we have the equation we have seen before, the green function equation written in terms of a green function for the non-interacting system and a self-energy, where the self-energy is given again by the green function, the screen potential, and this vertex gamma here. And then we have an equation for the screen potential that includes the response of the system, so the polarization of the system that we've seen before graphically, and the equations for the rest of these vertices in this pentagon, in the Edin's pentagon. So this would be the representation using Feynman diagrams. Again, we see the grid function written in terms of the grid function of a non-interacting system and the self-energy, and the rest of the equations. So we can start, if we want to solve Edin's equation, we'll start, let's say, from a a first guess for the green function, and then we'll have or a first guess also for the self-energy, and we'll solve this equation here, where the green function gives the propagation of our particle. Then we rotate the pentagon. We have to solve this vertex here, again in terms of the self-energy and the green function. And this vertex here, that is, let's say, the complicated part of it is, includes like an effective electron-hole interaction that we'll see that we'll neglect in the GW calculation. We have our response function, the screened interaction between our quasiparticles and the self-energy. And we'll go back, we'll rotate the pentagon and go back to the first equation. So we don't solve these equations as I showed before. We neglect this vertex here that we say that is 1. So we simplify the response function that is now given just in terms of the one particle green function. So the GW approximation corresponds to solving the equations in this set of equations. It's still an interactive procedure, but again, so this would be the corresponding diagrams of this cutted pentagon. And as we see here, this GW equation, we see that the self-energy is simply given by the green function and the spin potential. That gives the name to the approximation. And not only we usually neglect this vertex here, we also usually don't do the whole iterative process. We do a one-shot G0 W0 calculation. What does this mean? And maybe this gets us closer to the answer of the question than before. We start. So our starting point usually is a mean field calculation, like a DFT calculation. We use the calculation, the energies that come from that mean field calculation, that here I consider the DFT calculation. So these are quantum energies to construct the non-interacting green function. And we say that our green function is given by the non-interacting green function. We use it to compute the response function that will enter in the screen Coulomb potential, and that will finally give us our self-energy. So the self-energy is like what we are looking for to compute. And so this self-energy, if you recall from the previous slides, is the property that will give us the structure of our spectral function. So now, usually, what we want is we have a DFT band structure. We want to correct this band structure. We want to compute the interacting system band structure, and we compute it as I said before, as a correction to the non-interacting band structure. And this is given. So in the end, what we get from the self-energy is that we can write an equation that gives us a correction to our energy states that will give us the band structure, and it's a correction based on the original midfield values, the quantum values, and the correction that will be given by the self-energy. But this will be very well explained by Alberto and Giacomo in the next sessions. So the result of a practical equation usually is that we compute the correction to a mean field band structure, and we can see here this is the band structure for bulk HBN, and we have the original mean field band structure calculated probably with DFT, and then the GW calculation will give us the correction to this band structure that shifts the energy of the bands in the way that we can see here. So I have no idea how long I've been. So, wait, 5 minutes? Okay. So in a, let's say, very mixed and graphical way, I try to explain you like the most fundamental elements of a GW calculation. That would be like the quasi-particle excitation energies and this screened Coulomb interaction. So if we do a parallel in the DFT with a mean field calculation, for instance, a DFT calculation, we have our original N particle systems. These particles interact. In DFT, we map these particles in a non-interacting system, and we put all the interactions in this exchange and correlation potential. That is a local and does not depend on the frequency. While if, and then we get ground state properties of the system. Like a DFT band structure that does not correspond to what we, for instance, measure in a photoemission experiment. If we do a GW calculation, what we do is this first remapping in a system of quasi-particles, and we consider the screened interaction, Coulomb interaction, this W here. And so now the complicated part is inside. So all the scattering events are inside this self-energy here. That is much complicated because it's not local, it's dynamic. But what we get as an extra with respect to DFT calculation, and that we have now excited state properties. And by excited state properties, I mean the band structure that we measure with photoemission. That is an excited property. It's not a ground state property. But in practice, even if we usually separate these methods, when we do a GW calculation, very often we start by a DFT calculation. We use it to construct a non-interacting green function that will then give us a correction to our original DFT band structure. And that correction is contained in this self-energy here. So I will finish very quickly. Of course, GW approximation is an approximation, and it is very efficient. And of course, the most well-known successful story is the correction of the band gaps for semiconductors. So we have here a plot where we see the results of the band gaps for different systems with respect to the experimental band gap, to the measured band gap, and we see that GW corrects the DFT results and gives better semiconductor band structure. So this is the most well-known success of the GW calculation, and it works and it's useful in many applications. Of course, as an approximation, it has limitations. So for instance, if we do the calculation as I described before, it's dependent on the initial state, on our DFT calculation. For instance, if we are using pseudopotentials, depends on what electrons are considered valence electrons, or what electrons are considered core electrons. It can give different results at the GW level. It depends on the exchange correlation potentials. For instance, if you have a material that is described in with one exchange and correlation potential as a conductor, and by another potential it gives you a semiconductor, then probably the GW calculation will not correctly distinguish between the two cases. So this print interaction has a self-screening inside that also can cause problems in some cases. Often it gives the wrong position of the satellites. Often it fails to describe the presence of multi-satellites in the spectral function. But of course, we can go beyond DFT. beyond FT. Beyond GW, we can go beyond GW, G0, W0. For instance, we can do some consistence or add vertex correction or use other techniques like cumulative expansions. And I'll leave it just like this as a perspective. So afterwards, you will hear all this again, but the questions very well written and explain how we in practice solve all these problems.
Thank you very much, Claudia. Time for questions.
So why we manipulate? Well, we are. I think the first motivation is because this is very complicated to compute. So if it's hard to compute and we can get away without computing it, it's okay. And probably because it's a good enough approximation if we neglect, in some cases, this interaction between hole and electrons in the system. So, but I think the first motivation is it's complicated. You have to compute how the self-energy varies with the green function. So that's the first. I don't know if you want to add something.
No, I mean, this is the GW approximation. The approximation.
Yeah, I listen, agree with you for the importance of the installations are not very body normal is the one that we discussed in the lecture. Even the people approach with the shrinker approach, so it's with method. A different way to solve to obtain in a closed form or many body functionality. But it's not ever happens. And there is no cons. The pro is that as Anya was mentioning, you will like from the beginning in terms of the string interaction. So it appears suddenly immediately the string interaction that is there at all orders of the installation. So you are arriving at the implementation of the allowing, oh, I have just interaction, just screen, the very interaction appears. Then you say, wow. So if it appears as the word is reaching again high orders in the screen interaction, I mean, the quasiparticle function naturally leads to the vertex one because you provide everything in terms of the curvature of the screen interaction. It's a key step of the installation. On the other hand, and you can try yourself, you want to redeem from an equation to obtain the matrix, no way. So it's very easy. You can see the electric approach to the main battery. Again, electrics is my physics, it's my mainly I want to describe the electrics for start. I mean, as investment and Greek theory, this is the equations.
And then that question.
Thank you for the note. There was, I mentioned in the previous talk about the development of this formalism. It was mainly the time played a role of serial time instead of the real time. But then here and started in this Fourier transform to the frequency time and start comparing with the actual experiments like observation and transformation. And there's a simplification for that.
I mean, she did Fourier transform. I mean, the special function of the volume. That's energy. You're perfectly okay with that. I mean, what we have to be careful to interpret, I mean, this is something written backwards, for example. The width of the peaks of formation, say, oh, the reverse of the population. Well, anybody can give you energy determination, so that's the energy, the width. That's perfectly okay in anybody. Absolutely, absolutely. In the point that in these equations, you don't see explicitly Gerber theory. It never appears. So there you may think the time in this equation is enough, but it's not. It's not. It's not. If you have Fourier transform, you need value We need to try something to do that. We would never see time, never, just frequency. Absolutely. Well,
We had some better software with time.
oh, yes, but that is, yes, it's true, but then there is so many bodies, that's a matter of approach. But within some many bodies, GR, within some figure, you would see frequency, just frequency.
I think the time difference between surface physical properties exactly, we're going to see the daytime of the absolute time evolution of that dimension is the one related to the construction using the gamma theorem. But that is an auxiliary time dependent you use to improve the particle from the non-graphical state, the graphical state, and so on and so forth. But then that is different devices. But that is an auxiliary time dependence, while this is the physical time dependence.